So we're talking today about what's called the angle addition formulae, and it's formulae in the plural because there's more than one of them. The angle addition formula. And I want you to take yourself back, well you can't, but I want you to picture that you are back at school with me, back in the 80s when I was doing A-level maths. We did have scientific calculators, but we also had to, we had a non-calculated paper, so we had to use tables to look up all sorts of things. Now you have tables in your formula book for binomial probabilities, and only a few years ago people were still using those. But I used to have to look up the values of sine and cos and tan, and even for multiplying large numbers I had to use log tables, which used the rules of logarithms to multiply two large numbers together by logging them, adding them and unlogging them. So take yourself back to those days. In those days we knew that things like 45 degrees and 60 degrees, they've got nice round values of sine and cos. Tan is always a bit more complicated, although tan 45 is quite a nice one. But yeah, they've got nice round values. So my question to you is, if I knew, or it was easy to remember the sine of 45 and the sine of 60, can I just add them together to get the sine of 105? No. Joe suggests no. Do we have anyone wanting to argue with him or agree with him?
They're not linear, so you can't.
You've hit the nail on the head, and in fact, sine 105, I mean, if I plot the graph of sine, we've got, this is 90, sorry, this is 180, sorry, so that's 90. So, 45 and 60 are sort of around here, but yes, 105 is on the way back down again. So yes, you're absolutely right, you can't just add the sine of 45 and the sine of 60 together to get the sine of 105. But the sine curve and the cos curve and the tan curve, there is a pattern there is a symmetry there. So is it in any way predictable? Is there any way of working out the sine of something like 105 if I know two numbers that add together to make it? And the answer is yes. And the great news is we're not required to remember it because it's printed in the formula book. So if you turn to page 5 in your formula books, and I don't know if Aidan and Joe, you're happy to... I think actually I might have another one. Hang on, I might have another one. I'll do one each.
I'm not too close.
And you will need to refer to it throughout the lesson, so it's good if you're... There you go. So you should see on page 5, at the top where it says trigonometric identities, you've got a funny looking thing that says sine and then in brackets a plus or minus b. And sorry, it's not on page 5 at all, is it? It's on page 6, I apologise. And what they're doing here is they're being very lazy. They're giving us two formula in one go. So they're giving us a formula for the sine of a plus b and a minus b in one go. Why they don't write them as two separate formula, I don't know. But I'm going to use those to work out the sine of 105, or rather you are. So the sine of one angle added to another angle, sine a plus b, is equal to the sine of a multiplied by the cos of b plus the cos of a multiplied by the sine of b. So I'm going to use that to work out the sine of 105 by making a equal to 45 and b equal to 60. So I'm going to do the sine of 45 multiplied by the cos of 60 added to the cos of 45 multiplied by the sine of 60. Now there is a proof for this. And you're expected to have a sort of a working knowledge of the proof, but I'm not expected to derive it in the same way that, say, we're expected to do proof by of differentiation by first principles. So go on, with only using your calculator to look up the sine and cos of 45 and 60, but doing the rest manually, see if you can use that formula to tell me what the sine of 105 is. And then, can you tell me what the cos of 15 is in a similar way? Okay, so the sine of 45 and the cos of 15 degrees. Using so the only thing you're allowed to do is look up the sine of 45, the sine of 60, the cos of 45 and the cos of 60. Unless you already know, in which case you can just peel them off.
Circular parabola.
Yes, certainly. Now you might be thinking, well, hang on a minute, why are we bothering to do this? But the main benefit, the main advantage of the A plus B rules is what happens when we make A and B both the same. That's where it really kicks in and is beneficial, because it gives us formulas for doubling angles, but we're not going to do that today. So this is basically a surd question. I'm asking you to do some surd arithmetic, because you're going to get calculations that involve surds. But you should get the same answer that we get when we then actually just type in sine 105. Make sure you calculate it in degrees, but these formulas work in both degrees and radians.
What you said we need to have a working knowledge
Of where it comes from.
Yeah.
We're not going to do that today. It's in the textbook if you want to
I
look
don't
it up.
know if it's recorded. I can't see in the picture.
Sorry?
It's just a red light.
Yes, that's recording. It's recording. Yeah. No, the screen goes off just to save energy, save battery. Formula on the formula sheet, so nothing to remember. You can do cos of 15 for me, making sure you read the formula carefully.
So if you pick any values, what do
Yes.
you want us to do? B minus A
Yes.
for this one?
Yes.
Okay.
So it would be sensible to make
A60.
A60 and B.
Why didn't I can get away doing just plus 15 in the calculator?
Well, I absolutely understand, and you can. There are these are relics from the past, but they set up the final trig identities, which are very useful. So we're sort of in an intermediate stage at the moment where we are we're sort of setting up the next set of identities. Just run with it for now. Make sure you calculate it in radians. Sorry, in degrees.
For the cos one, is it minus for angles?
Yeah, so you've got to look at the way the signs are. So for cos A minus B, you've got a plus in between, haven't you? So when you're reading cos A minus B, you use the sign that's on the bottom, which is plus. So it's a really funny way of writing it, and I'm sure it's been confusing people since the dawn of time. But So if you type in sine 105 on your calculator, it does tell you it's, I forget which way around it does it, but it's root 2 plus root 6 over 4, which is what we get from the calculation using the formula. And I'm going to do cos 15 using cos A minus B, where A is 60 and B is 45. You can do it with any angle. It works for any angle. It doesn't only work for 60 and 45, and it doesn't just work for those nice round values like 30 and 90. It works for any value. Genuinely, I don't remember it because it's on the formula sheet. So that's cos A cos B plus sine A sine B. Okay, if you look at the way the formula is, when you're doing cos A minus B, the minus is on the bottom, so you use the sign from the bottom, which is a plus. But you end up with the same sum, don't you? You end up with a half times 2 root 2, root 2 over 2, sorry, and you end up with root 2 over 2 times root 3 over 2. So you actually get the same answer as we got before.
Same answer as what?
As sine 105, cos 15 and sine 105. Same answer.
Is that how that works?
Because sine 105,
What have I done wrong?
no.
Okay. So how on earth do they stretch this into a sort of exam question, given the fact that you've got these lovely calculators which will do it for you anyway? Okay. So well, we haven't done anything with the tan A plus B formula. So here's a question using the tan A plus B formula. As always, tan is always more complicated, but the formulas are there. So tan of A plus B, and you've got to make sure you get the signs the right way up. That's the tan of A plus the tan of B over 1 minus tan A times tan B. And that thing on the formula sheet that says A plus B doesn't equal, that's just saying it can't be equal to one of those values where tan isn't defined, because tan isn't defined at minus 90 and plus 90 and 270 and what have you. So go on, just see if you can answer that. So they firstly, in part A, just want you to write out the formula with tan A and tan B, and then they want you to plug in the values of tan 45 and tan 30. That's all they're asking you to do. So this is an algebra question. It's a surd question.
What's that weird thing at the end?
Sorry?
What's the weird thing?
It's a weird thing.
What's the weird thing at the end of the time one?
It's just saying A plus B isn't allowed to add up to one of those angles where tan isn't defined. So tan isn't defined at 90. So it's just saying A plus B can't be 90, and it can't be 270, and it can't be any other angle. So I'm just going to copy out the formula for part A. That's all I'm going to do, making sure I get the signs right. Then I'm going to look up the tan of 45, and I'm going to look up the tan of 30 on my calculator, and I'm going to plug them in and try and make the answer equal 2 plus root 3. That's all we're doing. So this is a surd question. Nothing more, nothing less. So the only tans you're allowed to look up are 45 and 30. Joe, what would your proposal be at this point? There's a couple of ways we could go. So what would your proposal be for the next step? We've got to make it look like 2 plus root 3. So that's what we're aiming for. And I've got it to here by just substituting the values in.
Ugly cousin technique.
Say again, sorry?
Ugly cousin technique. What's it called? Ugly twin technique? Where you do like.
Ugly
plus.
twin technique?
Yeah, like it's like 1 plus.
Oh right, you want to multiply by... Where have you come across that?
That's what you told me.
I call it the ugly twin.
The ugly like stepsister.
Oh right, I'm sorry.
What's
No,
that before?
well, yeah, not in this context. Yeah, no, it's the, yeah, you could multiply by 1 plus 3 root 3 over 3. I don't know, it's just a bit hard. So, knowing me, what am I most likely to do first here? Particularly for how I feel about fractions. I'm going to multiply everything by 3. Now, that's not me doing what I do to equations, where I multiply both sides by 3, because this isn't an equation, this is a fraction. This is me basically sort of doing what we do when we do this. We're multiplying the top and the bottom of the fraction by 3. So I'm going to do that to this fraction. I'm going to multiply the top and the bottom by 3. It's the same fraction then. So that becomes 3, that becomes root 3, that becomes 3, and that becomes root 3. And now I can use the ugly stepsister approach, which
You've definitely got that.
well, I know I use that phrase sometimes, but I never thought I'd used it in this context. Because we want to rationalise the denominator, don't we? We're asked to turn it into this, so there's a rationalising the denominator to be done there. And you've got to grid that out, haven't you? So just, if you haven't done that, grid that out and make sure that gives you the correct answer. Page 70, sorry, 170, questions 7 and 8 are where we're going next. But I think it's definitely worth doing this because, you know, surd practice is worthwhile practice. So once you've done that, page 170, 7 and 8 would be where I would go next. But sort of finish that one off first. You've got to make it look like 2 plus root 3.
What was that question?
So that the question we are doing is on page 173, this one, but the one I want you to do after that, I mean, we're nearly done with that one, is on page 170. So when I do that, I get on the top 12 plus 6 root 3, and on the bottom I get 6. Because the reason we do this technique is to remove the surds from the bottom. Root 3 times root 3, remember, is 3, and minus root 3 times root 3 is minus 3. And 2 things divided by 1 thing. Page 170, questions 7 and 8. Here you've got one angle you do know and one you don't, so you're going to have some algebra in your answer. It's just using the formula, just familiarising you with the formula. Page 170 now?
Yeah. I've done this stuff.
You've done this stuff?
Yeah, preparation for exams and stuff.
Okay, page 173, question 6 is the next one. It's all good stuff, Matt. Don't do you any harm. Or you could just learn to read questions properly. That'd be good practice. I'm going to write those here. I've rewritten them there.
What's this carrying on from?
So the last bit of trig that we did was the reciprocal identities, where you took sine squared x plus cos squared x equals 1, and divided everything by sine squared, and then divided everything by cos squared. Sorry?
What was that last bit? That's do I know from the wall?
It'd be in your notes, look back in your notes. So before we did moments, it was part of the work we did on sec, cosec and cot. Okay? So this is not sec, cosec and cot, but it's the next step along the way of trig. Did you notice that your calculator needs to be switched back into radians for this question?
I don't understand the question.
So the first thing you're going to do is write down the sine a plus b formula, and you're going to make a equal to x and b equal to pi over 6. And then you're just going to substitute in cos pi over 6 and sine pi over 6.
And this is in radians.
And how do we know it's in radians, George?
It's got
Yeah, it's nasty, isn't it? There's no clue given at all. But yes, you're absolutely right. So these are all just sort of little, 1 mark, 2 mark questions aimed to test your understanding of the way the formulas work. You'd never get a question on its own like this, but it might be a part A or leading on to a more complicated question. I say you need to switch character back into radians, or you can remember that pi over 6 is 30 degrees, of course, which is maybe quicker. So that's all they're after. That's all they're after. Simple as that.
When did you do that?
I just substitute in the value of sine of pi over 6 and cos pi over 6. Cos pi over 6 is root 3 over 2. Sine pi over 6 is half. question 8 is very similar, so you may feel you can skip that and go straight to page 173, question 6.
What about 8?
Sorry?
What about 8?
Well, 8 is very similar to 7, so I can show you the answer to number 8 if you want. So hopefully, so we've got just pi over 3 is 60 degrees, so it's very, very similar sort of question. So can we just pause on number 6? We're asked to work out the value of sine A plus B in the first part, which requires me to know sine A and sine B, tick, but also cos A and cos B. Haven't got those, have I? So you need to remember the trick for working out cos when you know sine, and what we're not allowed to do is shift sine to get the angle and then cos it. Because it's a technique that uses the identities. It's another way of them getting us to use the identities. Your calculator will give you the right answer, but we're expected to show that we can do it the old-fashioned, the correct way. So the first thing to remember is the cast rule, which reminds us that between 0 and 90 degrees, all three, sine, cos and tan, are positive. The cast diagram reminds us which of the three trig ratios are positive where. So between 0 and 90 they all are. Between 90 and 180 only sine is positive, cos and tan are negative. Between 180 and 270 only tan is, and only cos is positive between 270 and 0. So what we do is we use the sine squared plus cos squared equals 1 identity. So if I know what sine is, sine squared is that squared, which would be 16 over 25. Therefore, cos squared A is 1 minus 16 over 25, which is 9 over 25. So cos A will be the square root of that. And when you square a fraction, you can just square it at the top and the bottom. Simple as that. And normally I would write plus or minus 3/5. However, we're told that they're acute, A and B. So I know that they're between 0 and 90, so I know it's positive. So I've got cos A is 3/5, which is positive. So the only thing you now need to work out is is cos of B using the same process. That's going to be a surd. So that little trick is expected of you. I know we're in a funny old world where some things you can do on your calculator, so you can use your calculator to solve quadratic equations and simultaneous equations, but this you'd be expected to show some method. Yes?
Isn't it just set in the question though?
It doesn't tell you what cos A and cos B are. And the sine A plus B formula uses both cos A and cos B.
Funny don't you just type in sine with this, see what happens?
Well, you can shift sign that and then cos it, yes, but I just said that's not the proper way of doing it, and although there are some things we are allowed to do in calculation, this is still one thing that you'd be expected to demonstrate. It's not complicated, is it?
It's just that positive. So it's been.
Well, work out cos b for me. Using this process. And then you can answer the question. Have you done part C? And did you get the answer they got in the book? Have you got a surd in your denominator in your answer? Oh, right. What's cos b? Come on. Waiting for you to fill that gap for me. Yeah. So we get so that gives us 3 plus 4 root 3, or 4 root 3 plus 3 over 10. A similar process gives you 4 plus 3 root 3 over 10. Sec is 1 over cos. And we'll look at the third letter. So 1 over cos, you just flip that answer. So you flip that answer and get 10 over 4 plus 3 root 3 for here. And all they've done here is they've then rationalised that by multiplying the top and the bottom by 4 minus 3 root 3, which seems a bit unnecessary really, but that's what they've done. So sec a minus b, there's not a formula for sec a minus b. We just work out cos a minus b, and then we just flip it, because sec is 1 over cos. Really is as simple as that. They've made it a bit unpleasant by making you rationalise it. We just do one more example. We'll do one more minute just to finish that off, and then we'll just do one more example before we leave it. So I've just said that for sec a minus b, there's not a formula for sec a minus b, so all you do is you take cos a minus b and just flip it. Right, so the other thing that maybe we'd be expected to do would be get involved in a bit of proof. So you remember these sorts of questions where we are asked to prove something and we choose which side we're going to fiddle with. we can either fiddle with the left-hand side or the right-hand side, but really we want to make one equal the other. Now I'm going to encourage you in this case to leave the right-hand side and consider the left-hand side, because it is much, much easier. It all falls out really nice and quickly if you do that. So look at the left-hand side. I can't help noticing the right-hand side is written as a single fraction, so see if you can make the left-hand side into a common denominator fraction subtraction sum.
So,
Yes, George.
these kind of proof questions, or this like more generally, if you manipulate both sides so that you get an answer at the end which is known to be true, so if you got like 5 equals 5, would that also be considered?
You'll be okay. The only thing I would say to be proper is if you manipulate the right hand side and then you manipulate the left hand side, you get something that's the same. Really what you should do is go like that and then like that. So you should manipulate your left hand side to equal 5 and then show how 5 can be manipulated to equal what you started with. See what I mean? So rather than going like that, try to go like that. But this one much more simple than that. But yeah, so I'm going to say consider left hand side. So Jacob, what's my common denominator going to be?
Sin b cos b.
So what do I need to multiply this side by?
Cos b.
And this side, sin b.
Sin b, yeah.
Then you can write it as a single, and I'm going to write it as sin b cos b. So I've got, it doesn't matter which way round you write that, cos a cos b minus sin a sin b. And then you could just say, oh, hang on a minute, I recognise that. Oh, it's the cos a plus b form. Simple as that. So going from there to there, you're not expected to do any work at all. You can just say, yeah, I recognise that. And that's it. Simple as that.